Hi everyone, I am Tawan Tinthawankun. Today, I would like to present about the development of an autonomous mango picking system using a 7 degree of freedom robot manipulator. This is my independent study project of my master degree in mechanical engineering focused on robotics, Chiang Mai University. This project is under the support of Associate Professor Dr. Thirapong Wongratanaphaisan, the founder of this degree program. This is a demo of the harvesting mango autonomously. It was tested in the real scenario in the real ocean. The robot could reach at the cutting point and then carry the crops into the basket automatically. Now, place the mango in the basket. So, why use a robot instead of letting the human do? I will show you about this point later. This is all my presentation content. I will start at the background about why this project was happened. And next, I will preview the related works for the ideas. Then, I will describe about the entire robot system. And then, I will propose about the approach for harvesting mango autonomously by using this platform. Then, I will show you the performance of the entire system during the test in the ocean. Finally, I will conclude all about my contributions and provide some suggestions for the future development. First, I would like to introduce all my background of this project. The inspiration was got from the real challenge in the mango industry. First are about the mango selection and wrapping. Those tasks require experienced laborer working on cutting the mango each by each to keep just the only one best. Then wrap it with the same color bag for just scheduling the harvesting date. Once the time is arrived the date, the farmer will harvest for the crops by the same color tag. Since those tasks are skill and labor-intensive tasks, the robot system has the potential to make those tasks done as the human could do. This will possibly reduce workers in the next era of our agriculture. In this project, I will contribute on two main topics. First, I will provide the mango bag detection, then obtain the cutting point at the stem. Next, I will provide the harvesting process using the robot arm together with the scissor gripper. Okay, as I need to implement all of this out tangibly, some previous work about the fruit segmentation and autonomous harvesting are very important for the ideas. This research team proposed the method to determine the picking point on the strawberry. They do instant segmentation on each strawberry fruit for the mass, and then estimate the stem axis in which it could split the mass by half symmetrically. Then, obsessing the point at the fruit pole upward along this stem axis, getting up the picking point. By the way, this solution is worked properly in case of the stem locates close to the fruit top center. This research team just modified the mass CNN algorithm by extending the mass branch for the key point detection. It works in parallel with the other branches. The output of this network branch are three key points. The first one is being the picking point, while the other two points are used to validate this picking point. By the way, it is possible to use the conventional mass CNN algorithm to obtain the mass of the mango. Then, just determine the cutting point on the stem upward this mass for the simplicity of our implementation. Next, the solution of cutting the stem with the machine is also very important. This research is about pruning the sweet cherry branch. The scissor gripper is mounted on the robot arm like here to cut the horizontal branch. This gripper used pneumatic actuator because it could provide massive force enough to cut the big stem. This project focused on the motion planning, so they defined the pruning point to the robot through their own GUI application manually. And they mainly focus on checking the collision in the environment, then did the motion planning without collisions. By the way, most of our mango crops have not occurred by any solid big stem, so we could define the fixed trajectory which does not collide with the environment as the preset. The other work is about pruning rose branch using the scissor gripper which mount on the robot arm. In this case, the gripper here is operated by just the electric motor since it provides enough cutting force for the small branches like the rose. Their strategy on finding the picking point is also very interesting. They move the robot arm through the pre-described trajectory like the grid in rectangle area. The arm is stopped at each grid corner doing the snapshot for the RGB frame data.
Then they combine the frame together for higher resolution of the row branch data. After that, they did image segmentation using an encoder-decoder CNN. Then, they obtain each point on the branches by offsetting the ground plane upward by the distance value, then obtain the point which placed on the plane as a pruning point. This is a great example of using mass image to obtain the pruning point on the stems. And this is evidence for us that it is possible to find the cutting point on the mango stem. In this section, I will describe all about the design and implementation for the entire system.
Let us start at the concept and design. Here's the robot arm with the gripper installed on the column lift. The electric cart is used for moving the equipment through the orchard for exporting the crops. The cart throttle is located at the cart handle like this, and the screen display is also installed at here. Here's our swing arm. Let us turn on the system. Release the emergency first to start move. Okay, push it forward. Then pull it backward. This is a motor and differential drivetrain. It's allowed to make the car turn it like this. Then initialize the robot system. Release the robot arm emergency stop and then reset its position. Okay, get it into the ready position. You can move the robot around like this. In the setting tab, you can turn on and off the gripper manually and disable the gripper if you want. Now control the column lift. You can use the external remote also. Now, let the robot do the harvesting task. Here we go. Cut it, then grabs it. Carry the bag into the basket. Okay, place it. Well done. And then it back to the search position. Okay, now it's to close the system. I will walk through the subsystem each by each, including the manipulator, the gripper, the cart, and the software. First, this is the robot arm with its controller. It's capable to control our custom gripper.
This arm could reach the target post repeatedly with just 0.1 mm maximum error. It could carry 3.5 load at the end effector joint and provide 1 meter per second maximum speed at the last joint end. Moreover, the controllers provide external GPIO interface for external devices and do some interaction with the robot directly. In our case, we will command our gripper through this interface.
Next, the column lift is selected for a 1000 mm in stroke.
It could move at 12 mm per second maximum speed. This device can handle 100 kg maximum axial load.
We combine the robot arm and the column lift together.
This is because we need to enhance the robot arm workspace in vertical direction, making it could reach the mango between 1.2 and 3.2 meters.
This robot arm could operate 770 diameter around. The Dana-Witt-Hartenberg parameter could be used to perform the transformation of the coordinate points between all the joints. This is our own design scissor gripper. It could cut the stem between 4 to 6 millimeters in diameter. The target could tolerate about 13 height and 26 depth from the scissor center. This lead screw is self-locking mechanism. It allows attaching the mango together with the gripper without electricity actuated at the motor.
About the hardware vision system, we have installed the Intel RealSense D345i on the top of the gripper. This is the proper position for observing for the stem in the front and above of the scissor. This camera installed inside the waterproof goggle to protect it out of the mist.
Here's the component inside the gripper. This includes scissor mechanism which contains the motor drive through the lead screw here. This is for move the blade, cut and release. The very tiny controller is also placed here. Let us dive into the controller process. The Hall effect sensors are installed at both ends of the mechanism. Those are for limiting the scissor blade on do cut and do release actions. We do the motor control using the PWM motor driver. The power supply is also sourced from the main robot battery. Then regulate down in many levels for each controller subcircuits.
In terms of command interface, it receives them from the robot arm controller through the connector and the end effector.
The gripper operates at this state machine diagram with the control loop frequency about 1 kHz and command the cut and release action through the 2 bits parallel data as this table.
Identify the command states containing stop, cut, release, and homing actions. About the position of the gripper, identify it using the limit switches status becoming in between, cut, detached positions. Once the limit switches status from the end of the mechanism are detected, the position become undefined state. Thus, the controller firmware will compare both command status together with the position status. If the position status does not match with the command status, the controller will actuate the gripper to the required position or terminate the operation in case of incoming command is stop. The other handler state also provided in case of the position status is undefined, so the controller always stop the gripper until the state is changed.
Here's the total device of the card handle. It is composed of 2 load cell devices connected in a half-bit circuit scheme. Here's it about the test in the straight direction. Now I pull it back and then I push it forward. Since we use the differential mechanism to drive those 2 wheels from the single motor, it allows the card rotate around this point, creating the left and right turning action. To turn this card around like this, you can just push or pull the throttle like this a little bit, and then you can rotate around easier. This is the hardware interface diagram. The signal from the half-bit load cell is amplified at this amplifier circuit, then pass it through the software first-order low-pass filter to smooth this signal. Then modify it with force profile and also apply the deadband before sending it to the motor drive as the PWM torque command. Those signal conditioning process result the smooth motion experience to the user during the card control. The power supply is also sourced from the main battery as similar as the gripper source, and then regulate it down in many levels for supplying to many subcircuits. The card operates at the state machine diagram, which are idle state, stop state, and moving states. When the emergency stop is pressed, the card is always stopped. Once it's released, then you could move the card forward and backward.
The controller will do reset on the load cell idle value after user release the emergency stop immediately. This is to prevent the load cell idle signal level change when leave it for a long time. So, user should place the card once parked it to prevent it moves unexpectedly.
Here's the software system that we use to manipulate all the robot tasks. The application contains 2 tabs, which are the operation window and the setting window. The detected mango results are displayed in the right-hand side, and the detection status is locked in the left-hand side. User can control the robot arm at the column lift and here, control the search operation at here, and let the robot start the harvesting task at here. In the setting tab, user can do the setting for the robot workspace, speed, and the harvesting strategy parameters at here, and setting the AI and gripper operation at here. The application is operated at this state machine diagram. The operation contains the idle state, searching for the back state, found the back state, and harvesting execution state. The state which is handle the error is also provided at here.
The application enters idle state first, doing the inference for the mango bag. Once user presses on the search operation button, the application will enter into mango bag searching state. The algorithm will calculate for the cutting points of the mango bags, then select most closest one to the gripper. I will describe this algorithm later in next chapter. After the calculation is done, if found the reachable mango bag, The application will wait for the user to confirm this task. Once user press on the Go button, the application will command the robot arm to do the harvesting task. If some error occurs during the task, the application will enter into the error state. Here, user must press on the reset button on the application to let the application back to active again.
This mini computer I will use to run the application software. I select this Intel NUC because it comes with an external GPU. This NVIDIA GPU is allow us to run the object segmentation model faster than running it on the CPU. Next, the touchscreen panel displays our program interface. User can interact with the system conveniently through this screen monitor by just touch it. Here are the libraries that I use as the application backend. They are about the GUI, object detection, and computer vision.
Our software GUI rely on the Qt library, which is the famous GUI library in the C++ world. It contains many application mechanisms for the desktop app implementation, so it provides us the convenience. The TensorFlow framework provides the inference environment for the mass CNN algorithm. This library relies on the NVIDIA CUDA toolkit that make it access for the hardware GPU capabilities. I use the tools in the OpenCV library for the image processing tasks in this application, and the Intel RealSense software development kit is used to communicate with the camera and do some calculations on the RGBD data. Finally, this application runs on the Ubuntu Linux OS.
I deploy this application in two ways. First, running as a system service during the startup.
And here, the system will enter the application window automatically after user presses on the computer power button.
And next, I also create the desktop icon. Here is the alternative way for user to access to our application manually.
Okay, now our journey is come into the key part of this project, which is about the implementation of the harvesting approach.
Here's the problem statement. I divide this into three main groups. First, there is the environment, including obstacle and target, which is the mango bag. Second, there is the robot system. I divide it into two groups based on the role of the operations. The red highlight here are the robot arm and gripper, which are operated by the software automatically. The purple highlight are column lift and electric cart, which requires human to control it manually. And the third is user. At the right-hand side image shows us the coordinates, which are mainly focused on this study.
This includes the target, the gripper, the camera, the robot arm, and the basket coordinates.
This is the condition of this study. I divide into two main sections. About the harvesting process, the purple components will operate by the user. The red component here must search for the crops and then execute the harvesting tasks automatically. Regarding the robot manipulation tasks, all the operations are done only in static environment. This means the robot arm could move only when the cart is parked. Lastly, the approachable mango bag must be located in the robot workspace only. This is the dataset I used to train the mass CNN model. This model I brought it from the existing mass CNN ResNet 50, which was trained with the Microsoft Cocoa dataset. Here, those 80% of the image dataset was used for fine-tuning the model. This could make the model know for both mango bags and mangoes.
And the benefit of using the fine-tuning approach is about the time saving, rather than constructing this deep neural network from scratch. Okay, the other 20% of those images are for the model validation. The validation set here will let us know the optimum error of the model on the inferencing task. This is to prevent the overfitting behavior which occurs at the training time for a while.
I do select the trained model from the iteration around 60,000. And here, the total loss on validation datasets is around the minimum level before it goes into the overfitting region. Those processes I did on the TensorFlow Object Detection API and then deployed it as the TensorFlow Frozen Graph Depth format. Now, I divide the approach of the mango bag harvesting into three main steps. First, is it to detect and segment out the mango bag. Second, finding the cutting point. And third, executing the harvesting tasks. For the mango bag detection, now we retrieve the data from the RGB camera. The stream-bit data provides us both color frame and depth frame data. We pass the color frame data through the MathCNN algorithm to find the mango bag location and its max image. At the depth frame data, We filter it with the temporal filter, which is like the low-pass filter for smoothing the depth value with the window size of h. The idea is to provide the cutting point could start at the top back near the stem. To obtain this coordinate, we use all the points inside the rectangular area to process out this position. Okay, we must construct this rectangular boundary first. Obtain the most top left point and most bottom right point at the mass boundary. The bottom point is far from the top point vertically by 1/10 of the mass height. Then, offset the top line downward by a distant value to avoid getting 3D points around the mass perimeter. Then, offset those points narrower like this. Now, we get this rectangular area boundary already. Then, the index of those pixels inside can be used to obtain the 3D points. And here, the pixel index of both color frame and depth frame are all the same. At this step, the algorithm will iterate over both frames to obtain the pixel position from the color frame and obtain the depth distance from the depth frame. Then, we scale up the pixel coordinate with the depth data using the principle of the pinhole camera model. This returns the position coordinate in the real-world scale. And here, this approach is applicable with our data because the frame from this infrared camera have no any distortion.
The intrinsic parameters contain image coordinate and focal length. Those two parameters are retrieved from the interior sense camera during initializing time because these parameters depend on each camera device, not on the released model.
Then, we apply this approach on all pixels inside this rectangular area. Then, append all the results in the storage at the 3D point list. Finally, we figure out the x and y position by calculating for its median. But the z position, we chose the minimum distance out of the set. After we got the top back position already, offset the point upward, getting the cutting point. The cutting point we just got in the last step is described on the camera frame of reference. We must transform it into the robot world frame coordinate first using the transformation matrices approach. In our software, about the equation at the right-hand side, we separate the calculation into the finding position vectors and rotation matrices.
First, we transform the cutting point vector, which described on the camera frame of reference, into the gripper frame of reference using the vector distance between the camera and the gripper as in equation 1 and 2. Then, ask the robot controller for the current gripper orientations as in equation 3. Then, construct the rotation matrices separately in row, pitch, and yaw from the gripper frame to the robot world frame of reference as in equation 4 to 6. Then combine those together as in equation 7. Finally, obtain the gripper position from the robot arm controller and then apply the transformation on the cutting point with respect to the gripper into the robot world frame of reference as in equation 8.
During the harvesting time, we need the robot move in front of the stem first before reaching the cutting point. This position we call an approaching point. This point is the offset point of the cutting point backward along with the axis between cutting point and the robot world frame coordinates. This operation is done on the top plane only, which means only the x and y element, while the z element as similar as in the cutting point. Next, we check on both cutting point and approaching point whether it located inside or outside the workspace. This workspace is for making sure that our configuration of those points will not collide with the other components.
In case of at least one of those points located outside the workspace, the algorithm will terminate the task, so letting the user start searching for the mango in more proper positions again.
Now, we let the robot move to the cutting point and then carry the mango into the basket safely. This is the position sequences of the harvesting process. Here, the green angle search is the robot configuration for searching the mango bag.
The other yellow positions are the post-approach and post-target that I took it from the points I described recently.
Then, we let the robot move in the joint mode and task mode, depending on the target type, either joint position or gripper in the effector pose.
First, the position naming starts with angles. I define that it is the robot joint angle position goal. The motion planning for reaching this kind of position is letting the robot arm moving in the joint mode. Here, the robot arm itself will do trajectory planning for each joint with its own motion profile, which are position, velocity, acceleration, and jerk profiles. Then execute the joint moves for the motion. Second, the position naming start with pose means the gripper and effector pose go. The motion planning here calls the task mode. The robot arm itself will apply the motion profile between the current pose and pose go. Then it does the inward kinematics on each point in between, turning out the joint positions and then execute it happening.
All the points recently are defined as in this table. First, the green angle search is the templated position. User can adjust the robot arm to rotate around through this GUI interface. Next, the pose target is cutting point. To create both yellow pose, we just adding the orientation into approaching point and cutting points. The orientation about Z-axis dependent on the angle search position. The other white angle and poses are all the constant points.
Those goal points were designed during turn the robot arm into teach mode with collision concerns. In this mode, we constructed each white angle's point by adjusting the robot arm for each posture by hand. Then, read the robot current joint position, becoming each white angle joint positions. Okay, after we implemented the entire system already, now I will show you about the test on the platform and the algorithm for the performance.
In the first section, we test the operation of the electric cart, the robot arm, and the software GUI interface. In the real all-shot test, the cart could provide smooth motion in straight direction for both forward and backward moves. To turn the cart left and right, it requires user to take more force at the hand, and the suspension systems work properly on the difference of the terrains. About the robot arm test, it could reach the mango targets that located on the level height. By the way, we wrap the arm with this blue vinyl like this to protect the arm out of the mist. On the GUI display test, we could interact with the screen conveniently. If this improper operates under the very bright sunlight, the solution is to use the computer box to enclose the display out of the direct sunlight for more visibility.
This is the harvesting performance test of the autonomous system. We tested on 66 rapid mango samples. First, the algorithm could achieve 78% of reaching the stem. Then, the gripper could cut all the points successfully, but not all the mango could be attached on the gripper. The gripper could just grab the mango successfully by 78%. Then, there are only 3/4 of the samples which was carried into the basket successfully. For me, the interested topic is what was happening on 25% failure cases. Let us take a look at each scenario. In the first failure case, the system obtained wrong cutting point because of the masking error, so the cutting point was obtained at the other place instead of at the stem. The second failure happened because the gripper could not provide enough force to hold the stem with which diameter under 3 mm, so it fell down after cut like this. The last failure case occurred because the gripper could not attach the stem with enough force during the arm start move. Okay, now we are coming into the end. I would like to conclude all about the contribution of this work. Okay, first, the mobile platform could reach the mango cross within 1 meter, and it's capable to harvest mango located between 1.2 to 3.2 meters in height. Second, the algorithm could reach the mango stem by 78% success rate, and harvest the mangoes by 75% success rate. Now, I would like to propose the further development for some issues. About the mobile cart platform, the cart steer should be improved for better smooth motion, and the column lift speed must be improved, for example, 10 times over than current. About the harvesting algorithm, the gripper attached force must be raised for wider size range of the stem. The speed of the robot arm must be increased. This can make the harvesting task run faster. Finally, the algorithm must provide more accuracy on the cutting point. Okay, the presentation is end. Thank you for your cooperation. If you have any question, feel free to discuss with me through this email. Thank you.